Hello friends, welcome to what should be the final lecture of the introductory module. Now we began this module by trying to define what minerals are. So in order to do that, we distinguished minerals as a category of substances that are available on the surface of the earth from the rest of the substances that are available. So we distinguished these minerals from the rest that are available on the earth's surface. Now, one of the distinguishing factors that we found or that we attributed to minerals is that the entities, they can be atoms or ions that constitute a mineral, they are regularly arranged. In other words, they exhibit a long range regular arrangement within a mineral. These entities that constitute a mineral, they exhibit rather a long range regular arrangement. We saw in the previous lecture, we spent quite some time on discussing what long range is, what a regular arrangement is, and in the previous lecture we wanted to relate, or we wanted to see how this long range arrangement or long range regular arrangement rather manifests itself in the properties or the behavior that we observe in a mineral. So that is what we got into in the previous lecture. Now essentially the reason we need to consider certain properties of the mineral is because they play a critical role when we are processing it. So ultimately our goal is to process a mineral. So we want to process a different wide range of minerals, and these processing techniques, these are devised based on the behavior or the properties of the minerals. So that's the reason why we spend some time on factors that govern the properties. So one of these factors is that the minerals exhibit a long range arrangement. So that's the reason why we spent quite some time on understanding what a long range regular arrangement is. And we also saw that the other factor rather that governs the properties of the mineral is the bonds that exist between these entities that constitute a mineral. So these are the factors that govern the properties of a mineral. And now we want to see what are the different properties that we observe in a mineral that are relevant to its processing. So in the previous lecture we began by considering one of the physical property. So in the previous lecture we saw we considered one of the physical property rather, that is density. So this property is fairly known to most of you, and it is rather not a specific or a technical term. It is widely used in our colloquial conversation as well. So density is nothing but it's rather the ratio of mass and volume. So what density essentially it quantifies is that for a given volume, what is the mass of the material. So for instance, if you consider two materials of a specific volume, so what is the mass that can be that are associated with this two different materials. So if you have a constant volume, so if you assume that both these materials are of unit volume, then the density is largely governed by the mass of the material. So density then can be defined as the mass of the material that per unit volume. So this is rather the physical property of a material, or in the context of mineral, it is a physical property of a mineral. Given that it considers the ratio of mass and volume, the unit that can conventionally be used is kg per meter cube. Now, when we want to compare a wide range of minerals, one with say mass in the range of kg and one with the mass in the range of grams, it is ideal when we are talking across a different range of minerals that exhibit a wide range of densities. It is rather comfortable when we are dealing with a parameter that is dimensionless. So that just by looking into the parameter, we would be able to distinguish which mineral is much denser than the other. So we would like to, for a discussion that encompasses a wide range of materials, we would like to have a parameter that is dimensionless. So therefore, what is usually done in such a case is that such a quantity is normalized and turned into dimensionless. So it is done by again taking the ratio of the similar quantity for a known material. So essentially the physical property that we are desiring, or the property that we need to understand, is density, and it has a specific unit, and we need to get rid of this unit because we want to consider a wide range of minerals. So in order to do that, what essentially needs to be done is we need to normalize this particular parameter. So in order to normalize it, in order to non-dimensionalize it, you consider the density of a known material and then take the ratio of the density of the material, the mineral that you are studying, and the density of the known material. And when we do so, what we end up is a non-dimensional representation of this quantity here. So now, when we take, if we consider this known material that with which we are going to normalize the density of a mineral as water. So when you attempt to normalize the density of a mineral using the density of water, then the corresponding density, the corresponding non-dimensionalized form of density is referred to as the specific gravity. So you have to define density, it has a specific unit, now you want to get rid of that unit, so you are then taking the ratio of the density of the known material, that is water, and the density of the mineral that you are considering, and this ratio renders you specific gravity. So the expression for the specific gravity, see, supposing we are focusing on a mineral Gm, so this is the mineral, M is the mineral we are focusing on. The specific gravity of this mineral is the ratio of the density of the mineral and the density of the water. So this is what the description of specific gravity is. Now, if you treat, instead of this conventional representation or conventional use of units, if you treat the unit of density, or if you consider the density in terms of grams per centimeter cube, if you make such a treatment, and since the density of water in terms of grams per centimeter cube is 1 gram per centimeter cube, because of this condition here, what you essentially end up having is that the magnitude of the density of the mineral will be equal to its specific gravity when you treat the unit of the density in grams per centimeter cube. So this translation between density to specific gravity is made easier when you consider, when you assume, instead of kg per meter cube, instead of kilogram per meter cube, when you consider gram per centimeter cube. The reason why this translation from density to specific gravity is made easier because the density of water is unit, it's just 1 gram per centimeter cube, and therefore when you use such a treatment and use that treatment in identifying the specific gravity, since these units cancel out each other, so you don't have to be worried about what unit you consider for each of these individual densities. It can be kg per meter cube, it can be gram per meter cube, but since in the calculation of specific gravity they cancel out each other, you end up having a condition where the magnitude of the specific gravity and the density of a mineral is equal. So of course the specific gravity will not have any dimension or any unit, but the magnitude will remain the same. Now it is important to note that even though you can vary the units or the treatment you render for the specific the density, that is, you can consider kg per meter cube or you can consider gram per meter cube, it is important to note that whatever unit you consider for the mineral, the same unit should be considered for the water as well. So when you do so, and when you assume a consistent gram per centimeter cube consideration, then you would realize that the specific gravity of a mineral and the density of the mineral will be equal. While we are considering different processing techniques, we will get to understand how relevant is this physical property of the mineral, how the physical property helps us process a given mineral. Apart from that, this physical property, that is density, also helps us understand the nature or the way in which a particular mineral is formed. So of course the minerals are formed through a natural process, but this natural process is not always the same. So they involve, as we saw in the previous lecture, a different combination of pressure and temperature. This combination of pressure and temperature can be realized by considering a density of the minerals. So what we mean by that is, when you have a mineral of a specific composition and it is formed at high pressure, then the density of that mineral will be higher when compared to a mineral that is formed in a relatively low pressure condition. So when the pressure is higher, the resulting density of the mineral will be higher. And in the same way, or rather in a different or in a contradictory manner, when the temperature at which a mineral forms is higher, then the density of the mineral, the resulting density of the mineral will be lower. So what essentially this relation helps us realize is that by considering the density of the minerals, we will be able to guess what is the combination of temperature and pressure involved during its formation. Supposing you are given two sets of minerals, or you are considering or comparing two minerals with different densities, you will be able to make an educated assumption on which mineral formed under a high pressure condition, which mineral formed at a low pressure condition, or if you want to talk in terms of temperature, or if it is a temperature that is the governing factor, we can say which mineral formed at a high temperature and which mineral rather formed at a low temperature. Now, this density, which is rather a macroscopic property, that is the property that you observe in a material while you observe its mass, you consider as volume. So these mass and volume are rather something that you can fairly associate with. So you know you have measured mass and you know what a volume is. So these are often referred to as the macroscopic properties. So these are properties that are rather relevant in a larger scale. So in a real world or real life situation, you are able to ascertain the mass of a given component, you are able to know its volume. So therefore these properties, or particularly this property, is a macroscopic physical property of the mineral. Now, if you want to consider the density of the mineral in an atomistic scale, so the equivalent property or equivalent parameter that helps us understand the density of a mineral in an atomistic scale is packing index. Supposing instead of discussing the density of the material or a density of a mineral in a physical scale, in a real life situation, if you want to discuss the density of a mineral in an atomistic scale, when you want to take a perspective from an atomic arrangements, then in such a situation, the equivalent term that helps us understand the density of the mineral from an atomistic standpoint, from the arrangement of the atom or ion, is packing index. The way we ascertain the packing index is by taking the ratio of the volume of the entities that are present in a given unit cell. So you consider a unit cell and you identify the number of entities that are present in this unit cell, and then you consider its volume and then take the ratio of the entire unit cell. So you consider a mineral, identify its regular arrangement, you study it, you characterize its regular arrangement, and from that you identify the unit cell, and in that unit cell you identify or you determine what is the equivalent number of entities that are present in the unit cell, calculate its volume, and then you take its ratio with respect to the volume of the unit cell. So it is the volume, or it's just the occupied volume of the unit cell. You have entities that are occupying this unit cell, and you are taking calculating the volume of this entities and then taking the ratio of the unit cell. So essentially what you are doing is you are considering not the volume of the entire unit cell, but rather the volume that is occupied by the entities within this unit cell. And this is expressed, since these are same parameters, they calculate both in the numerator and also in the denominator. What we are essentially calculating is the volume of the entity and the volume of the unit cell. This packing index is dimensionless, and we usually represent it as a percentage, so you multiply it with 100. So what essentially we have is, we have a representation of density in the atomistic scale. So when the packing index is higher, on the macroscopic level, on the level which is visible to us, the density is higher. When the packing index is lower, then correspondingly the density of that mineral will also be lower. So the formation of a mineral, the parameters, particularly pressure and temperature, that are involved in the formation of the mineral, can be realized from considering the density on the larger scale, on the macroscopic scale, that is just by considering a mineral, or by considering the packing index from the atomistic scale, by considering how much close these entities are arranged within a mineral. So from these we will be able to identify, or we will be able to make an educated assumption on what are the different combinations of pressure and temperature that are involved in the formation of a given mineral. Now, in addition to these physical properties, so there are other properties that are relevant for the processing of the minerals. So this is a physical property. So this involves mass, a physical property, and volume of a mineral, that is again a physical property. Now, in addition to this, there are other properties that are relevant when we are considering the processing of the minerals. So we will consider or move on to one such property, which is not a physical property but rather a mechanical property. So whatever we saw, that is the density that is relevant to us for mineral processing, is a physical property, and this is because it depends on the physical feature of how the entities in a mineral is arranged. Now, the next category of property or next sets of properties that we will be considering is the mechanical properties, because they depend on, the reason we distinguish density from these set of properties is because these largely depend on how the mineral responds to a mechanical condition which we impose. So the mechanical condition usually is some form of a load, and these properties largely deal with how a mineral responds to such a mechanical condition, to such a load. So the mechanical properties, the first one that is relevant to us is hardness. So these terms, again, some of you might be fairly familiar with, but for the benefit of all, I would be these terms will be refreshed. The definitions of these terms will be refreshed, and if there are any specific definition for this particular term in the context of minerals, it will be rather extended. So if you are familiar with this, maybe these thoughts might help you refresh your understanding. So hardness, in general terms, if you are considering for metals and alloys, so hardness is nothing but the resistance offered by a metal or an alloy to a local load. So you impose a local load, and this load, it offers a resistance to a permanent deformation. So the local load wants to permanently deform your material, and the resistance offered by the material is what we refer to as the hardness. So you have a local load. So supposing you have such a huge metal, and you apply a local load, meaning you have such a loading apparatus, and it is going to impose a local load here. Now this local load will try to introduce a permanent deformation into your material, and the resistance offered by your material to such a local permanent deformation is what we refer to as the hardness. Again, since this would be your first lecture, or this would be your course wherein you are introduced to certain concepts of metallurgical analysis, I am taking some time to explain or delineate rather what these terms involve, and that's the reason why, even though these might be redundant for some of you, or I don't know, most of you, please try to again try to brush up what your understanding is. So essentially, hardness is nothing but the resistance offered by a material to the local deformation that you are trying to attempt. So you are trying to locally, even though you have a large material, you are trying to locally deform it in this region, and the resistance offered by the material is what we refer to as the hardness. And the way we calculate it, this hardness, is by using a setup like this. You refer to this as intender, and the deformation that this intender achieves in the material, we refer to it as the intentation. So by measuring or by relating the load that is imposed by the intender and the intentation that is made within the material, you will be calculating the hardness of a metal or an alloy. So essentially, hardness, it defines the ability of a material to resist any plastic local permanent deformation, which can also be referred to as plastic. So this is what the definition of hardness is in the context of metals and alloys. So in order to do so, you try to introduce an indentation through an intender, and you try to relate the load and the indentation that is being formed. Now, in the context of minerals, the definition of hardness takes a different form. In the context of minerals, there are several reasons why we need to consider the context here, and this you will eventually understand maybe when you take up a course on mechanical behavior of materials, and you are trying to relate the concept that you have learned in physical metallurgy to mechanical behavior of material. You will understand why you need to take a different approach to understand the hardness of a mineral. So in the context of minerals, the hardness assumes a different form. In the context of minerals, hardness is the resistance offered by a mineral to scratches. So you attempt to introduce scratches on the surface of a mineral, and the resistance offered by the mineral to scratches is what we refer to as the hardness in the minerals. So instead of considering indentation, instead of considering local plastic deformation, this scratch hardness is what we determine, or what we are interested in when we are considering minerals. Unlike metals and alloys, wherein we are focused on indentation, intenders, local plastic deformation, in minerals we are focused on the resistance offered by the minerals to the scratches. So we want to understand how much resistance to a given scratch or given form of scratch is the material, or in a mineral is resistance to. So in order to do that, so there is a well established scale. So you have a well established scale from 1 to 10, wherein 1 represents a mineral that exhibits a least resistance, and 10 it refers to a mineral that exhibits a the utmost resistance. So you have a scale from 1 to 10 that is already being so it's often used as a reference scale. This scale is called as Mohs scale. So this scale is rather constructed by considering the range of a wide range of particularly 10 different minerals, and the scratch test has been conducted on them, and they are arranged in such a way that as you go along from 1 to 10, the scratch resistance is increasing. So you have a scale of reference, and this is called as Mohs scale. In the Mohs scale involves 10 different minerals, and in each of these minerals the scratch test has been conducted, and these minerals are arranged in such a way that when you move from 1 to 10, you are increasing the resistance offered by the mineral to scratch. So in the first place you have talc. This means talc offers the least amount of resistance to the scratches, and in the last place, on the 10th place, you have diamond, which offers the utmost resistance to the scratches. So essentially you have between 1 to 10 other 8 minerals. So essentially what you will be doing is, once you are able to identify the scratch resistance that is offered by a mineral, you will essentially be placing between these scales. So you have 1, 2, so on and so forth till 10, and depending, you compare the scratches that is observed in these reference materials to the one you are studying, and you will be placing it within this scale here. So essentially when you consider a kit that is available, that is given to you for performing this scratch test, you will be given all these 10 reference material, you will be conducting scratches in all these 10 reference material, and you will be conducting the scratch test in your material and comparing the scratches, and then placing it where you see, where you observe that the scratches are familiar. So that is how you ascertain the mechanical property of this particular mechanical property of a mineral, which is the scratch hardness. It is not the regular hardness, but rather it is scratch hardness. In addition to that, there are other conventional properties that are also considered, that are also studied while considering the mechanical properties of the mineral. There are also other mechanical properties that are relevant for processing a mineral. So one such mechanical property is brittleness. So again, these terms are, this term particularly here is rather, it is also used in our regular conversation. So we know that glass is brittle, meaning it rather breaks fairly easily. So that is what all it means in the context, in this context as well. So essentially what we understand by a mineral being brittle is that this mineral easily breaks. So this mineral fragments easily. So that is all that you need to understand in this particular context of mineral processing. So when you say that this particular mineral is brittle, it means we can fragment it rather easily. So when you apply a load, this mineral, instead of resisting or instead of behaving in a different manner, it just breaks into pieces. So that is what we mean by brittleness. And there is another term, that is another mineral property that that is rather relevant to our processing, that is malleability. So malleability by definition is the ability of a given mineral to be formed into sheets, to be transformed into sheets, or to be deformed into sheets. You have a mineral, the more you are able to change the shape of the mineral into a sheet, the more its malleability is, the more malleable it is. So malleability is nothing but the ability of a mineral, of a given mineral, to be drawn into sheets. So that is what we refer to as the malleability. So when you are able to, you have, say for instance, a cube of a mineral, and it is possible for you to stretch it as a sheet, then it means that particular mineral is rather highly malleable. If while doing so, the mineral, if it breaks off, if it fragments, then what we can refer to is that, or what we can attribute is that, that particular mineral is not, it's rather not that much malleable. So it is not malleable. Now there is also another mechanical properties. Again, these definitions, they are largely, we are talking in the context of mineral processing. These are not the standard objective definitions, but these are definitions that are relevant to us in the context of mineral processing. So therefore, malleability, ability of a mineral to be stretched into sheets, and ductility is the ability of a mineral to be drawn into wires. So like malleability, it involves stretching or transforming a given shape of a mineral to sheets. Ductility involves drawing a given shape of a mineral into wires. So this involves transforming the minerals into sheets. This informs transforming the minerals into wires. Again, these are contextual definition. These are rather fundamental definition in the context of mineral processing. When you are trying to draw a given mineral into wire, if it fails, it means it does not exhibit much ductility. But if you are able to successfully draw a given mineral into wires, then it means the mineral, that the given mineral is sufficiently ductile. And one other feature that you might not be familiar with, one other mechanical property that you might not be familiar with, but is of rather high relevance to us, or that is something that is uniquely observed in minerals, is sectarity. So sectarity is the ability of a particular material to be smoothly cut by a knife. So again, these are not a technical definition, but again a contextual definition. Supposing if you have a mineral that can be easily cut with a knife, can be smoothly cut with a knife, then we can refer to that mineral as sectile. So sectarity also can be categorized under the mechanical property, because we are imposing a load, we are imposing a mechanical condition, and we are seeing a response offered by the material. If we are able to cut smoothly a mineral using a sharp instrument, then it means that the mineral is sectile. Now we also have other conventional properties like elasticity and flexibility. Again, the contextual definition is, if you are attempting to deform your mineral, particularly deform it by bending it, stretching it, and any other form of deformation, you are trying to change its morphology. When the mineral gets back to its original form, then that mineral is elastic. You are operating in the elastic region, and the mineral exhibits a elasticity. On the other hand, if you are trying to bend a mineral and the mineral stays bent without breaking, you are trying to bend it, it stays bent but it is not fragmented, it is not broken, then that is referred to as flexibilities. So you have brittleness, malleability, ductility, sectarity, elasticity and flexibility. So these are, in addition to hardness, so these are they have specific definition in an objective sense. When you study these different properties in the context of a metal or an alloy, they have a specific definition, a well-established definition. However, in the context of mineral processing, we are considering it in relation to minerals, and therefore they have a specific definition in this context. These definitions might overlap, but for instance, in case of elasticity and sectarity, these definitions are largely unique, and particularly scratch hardness. So these definitions are largely unique, or they are largely characteristic of mineral processing. So in addition to physical properties like density, these properties, mechanical properties, that is a response of a mineral to an imposed condition, is also relevant for mineral processing. And in addition to that, these properties are governed by the two underpinning factors that we are familiar with. One is, these factors are governed by the bonding between the entities and the way in which these entities are arranged in a mineral. While we are considering how these properties are relevant to the processing of minerals, we will see what are the factors that dictate these properties? We will just have we will breeze over to see the relevance between these properties and the principle that govern them, or the factors that govern them, that is the arrangement of the entities and the bond between them, while we are considering how these properties are relevant. So when we are considering a specific processing technique, we will be this processing technique will be dependent on a specific property of the mineral, and there in that context we will see what or how this specific property is established in the mineral. So what are the underpinning factors that brings about this specific property rather in the mineral. Now, in addition to rather these different mechanical properties, there are also other properties that are also useful to us to develop a mineral processing technique. So we have seen a physical property of one of it, or one or two variants of it, and we have seen a few mechanical properties. So again, in addition to these mechanical properties, we also have another category or mechanical behavior, a form of a behavior of a mineral. So that is in response to a mechanical condition that will also help us in developing a processing technique. So that one of such behavior in response to a mechanical condition is referred to as cleavage. So what essentially this particular behavior, this cleavage, means is that in case of the regular arrangement of minerals or regular arrangement of entities in the minerals, it is possible that bonds between certain layers are weak when compared to others. So one of the primary example that we can think of, or one of the prime example that we can think of, is graphite. So if you consider the bond that exists between the entities, that is carbon within the graphite, along certain layers, the bond is very strong when compared to rest of the layers. So supposing if you view the regular arrangement of the entities in the form of layers, for instance, this is one way of viewing the arrangement of the entities in a material. So you can consider this view here. So let's assume that this is the top view. Now if you consider the same regular arrangement in the side view, what you would observe is just the arrangement of the ions in this manner. So layer by layer arrangement of the entities, and this is the side view here. And if you consider a top view, the view of this the way in which these entities are arranged will be in this manner. So let us consider the regular arrangement of the entities in a mineral. If you consider a top view, you will be able to observe an arrangement like this. If you consider a side view, you can translate the arrangement in this manner, the layer by layer arrangement. Now, if the bond in this view, or bond between the entities in this state, is stronger when compared to the bond that exists between the two different layers. So essentially what you have is, along a certain plane, the bond is rather stronger when compared to a different plane. So this is a plane that we would observe in case of the top view, and this here is the plane that is reflective of the side view. And along this plane, so between the two layers, the bond energy is different. The way the entities are bonded is different. The bond strength is different. So therefore, when you try to break or fragment a mineral, the fragmentation essentially occurs in between the layers which are weakly bonded, and that is what a cleavage refers to. So what a cleavage is, particularly in the context of minerals, what a cleavage is that whenever you try to break a mineral, whenever you try to fragment a mineral, almost always the fragmentation occurs along a particular plane. And this is what we refer to as cleavage. You take a pristine form of a mineral, a single crystal pristine form of a mineral. Now you apply a uniform load, and you always observe that the mineral breaks along a particular plane. So this is what we refer to as cleavage. The way cleavage is possible, the reason why we observe cleavage is because along a particular direction, or between particular layers of arrangements of the entities, we have weak bonding. So only when we have a weak bonding, only when you have the entities are bonded in rather they're tightly bonded, when they are loosely bonded along a certain planes or along a certain direction, in that direction, when you impose the load, the failure happens inevitably. So in that direction is alone, in that plane alone, the failure is observed. So that is what we refer to as cleavage. So in order for us to observe cleavage, we need to have weak bonding along between certain layer of atoms. And in that layer of atoms, in that plane is where you will observe the failure. Even if you consider a pristine mineral wherein you don't have any defects, you don't have any pre-existing cracks, even in such a condition, every time you impose a load, the mineral will fail along a particular plane, and that is what we refer to as cleavage. Now, the other form of failure that is rather quite opposite to cleavage is fracture. So, in case of cleavage, you observe the failure along a specific plane, and this specific plane is primarily because this specific plane is decided primarily because there is a weak bonding between the entities in that plane. So essentially, when you are trying to fragment a mineral, essentially you are trying to break the bonds between the entities. So the bonds between the entities are the ones that are holding this mineral together. So essentially, when you try to break it, you are trying to break the bonds between the entities. So supposing you have two ions that are holding the whole structure together, you have some, not just two ions, but all the ions are bonded to each other, and that is what holding a mineral together. And when you are breaking that mineral, you are essentially breaking that bond. Now, when you have in that mineral certain layers wherein the bond is weak, so it is this layer easily breaks off, thereby leading to cleavage. However, whenever you don't find such a bond, so no such weak bonding, then in such a case, the failure will depend on the type of load, the configuration of the load, or the components of the load that you are imposing. Depending on the way you are imposing the mechanical load, the failure would occur. So that is what we refer to as fracture. So in case of fracture, there is no weak bonding, there is no bond strength that is involved. Mostly all the entities exhibit more or less the same amount of bond strength. However, the failure occurs because you are imposing such a load condition. In case of fracture, the failure is largely because of the loading condition. So the failure largely reflects the loading condition. So that is one way the material fails when compared to cleavage. In case of cleavage, you have the failure occurring in a specific plane principally because of the weak bonding in that plane. In case of fracture, this happens because of the loading condition. Even though you might observe that even in fracture there is a failure along a particular plane, it is not because there is a weak bonding in that plane. It is because the fracture or the crack is easily propagating along that plane because of the loading condition. So the material either fails by cleavage or fracture. So the material, when you try to break it off, it fails either by cleavage or fracture. Of course, there can be other measures as well, but predominantly it fails either by cleavage or fracture. The cleavage involves the presence of weak bonding, and therefore even under pristine condition, what essentially happens is the material fails along a particular plane. In case of fracture, the plane which exhibits the failure is governed largely by the loading condition. Even in fracture you observe a failure along a particular plane, this is not because of weak bonding, this is largely reflective of the loading condition and the propagation of the cracks that ultimately leads to the fracture. So the characteristic feature of cleavage is the presence of weak bonding. In case of fracture, it is not the presence of weak bonding, it is the absence of weak bonding, and it is largely governed by the loading condition. So these are the mechanical properties that are relevant to us when we are trying to process the minerals. So we saw a physical property, we saw a combination of mechanical properties that are relevant to us, that are observed both in metals and in case of minerals as well, and now we need to distinguish between cleavage and fracture. Now, one other combination of properties that are relevant to us is magnetic properties of the minerals. So in addition to physical and mechanical properties, magnetic properties are also relevant to us when we are trying to process the minerals. So this magnetic property, what we mean by that? So what we mean by magnetic behavior of a mineral, where does it come from? So we saw that when you consider the subatomic arrangement of an entity in a mineral, it begins with shells. So what I mean by the subatomic entities or subatomic particles is basically electrons. So if you consider the electronic configuration of the entities that constitute a mineral, that is ions or atoms. These electrons they begin with they are arranged in shells, and these shells can be subdivided into subshells, and then you ultimately end up with orbitals. So if you recollect our discussion on covalent bonds, we saw what these orbitals are, and these orbitals, they accommodate 2 electrons, and these electrons, they exhibit opposite spin. So in your school days you would have seen how these electron spinning is being represented. So these are represented by these half arrows and pointing upwards and downwards. So this is how essentially you will represent the position or the availability of an electron in the orbital. So the way you would represent the presence of an electron in the orbital in this manner. So orbital can occupy a couple of electrons, and these couple of electrons, they cannot have a similar spinning, so they have opposite spinning. Now, if all the elements that constitute your minerals, so again the minerals are not often they do not comprise of an individual atom, they comprise of combinations of ions. If all the elements that constitute your minerals, so all the ions of the elements that constitute your minerals, in the orbitals of all the elements, they have electrons which are paired in this manner. So you have different elements that constitute your mineral, and the electronic configurations of all these elements are in such a way that they have this pair of electrons in the orbitals. In their orbitals, all these elements have pair of electrons which are spinning in the opposite directions. So you have different elements, and in orbitals of all the elements you have electrons that are spinning in the different directions. So ultimately, since it is the spinning of these electrons that results in the magnetic behavior, that results in the magnetic moment. Since you have the spinning in the opposite direction, they cancel out each other. So ultimately, you end up with no magnetic moment. So essentially, what you have is the magnetic moment of a mineral comes from the spinning of the electrons. So in the case wherein you have pair of electrons occupying every orbital of every element, and these electrons are spinning in the opposite direction, they cancel out each other, and therefore you have no magnetic moment. So magnetic moment is essentially comes from the spinning of electrons. When the spinning of electrons are in the opposite direction and they cancel out each other, you have no magnetic moment. And such a condition is what we refer to as the diamagnetism. So you have magnetic moment that arises from the rotation of electrons, and when you have the electrons that are distributed in the orbitals, you have pair of electrons in all the orbitals, and these are rotating in the opposite direction, you have no net magnetic moment, and this is what we refer to as the diamagnetism. Rotation leads to magnetic moment, opposite rotation cancels it out, no magnetic moment, diamagnetism. Now, it is not always the case that the orbitals have these paired electrons. It is possible that the orbital have unpaired electrons. And when you have such unpaired electrons, what essentially you don't have is you don't have a cancelling factors. Only when you have a paired electron, you have one electron that is rotating in the clockwise direction, the other electron rotating in the anti-clockwise direction, to say, and they cancel out each other, you have no net magnetic moment. However, when you have an unpaired electron, you don't have any counteracting rotation. You don't have any spinning that counteracts the moment that is created by the unpaired electron. So therefore, in case of orbitals with unpaired electron, if in your mineral you have elements with unpaired electron present in it, and since you don't have any other electron that could counteract its spinning, you have some degree of net magnetic moment. So the net magnetic moment is possible when you don't have these pair of electrons, but when you have a single electron that is exhibiting a spin in a particular direction, and you don't have any counteracting force, you have this net magnetic moment. And now when you have a net magnetic moment, this is within the entity. Now if this net magnetic moment should be observed all through the mineral, then this net magnetic moment should be aligned. So only when this net magnetic moment is aligned, you will observe. So all these net magnetic moment that is rendered by each and every individual entities will be collected, and it will be reflected as in the mineral as a whole. So you should have an unpaired electron to introduce net magnetic moment, and only if the net magnetic moment is aligned, you will be able to observe the magnetic moment in the mineral as a whole. If it is not aligned, then the net magnetic force is not that much efficient. It cancels out across the different entities, then you end up having a paramagnetic mineral. So even though individually the electron introduces a magnetic moment, since they are not aligned, so there is not a specific orientation in which this magnetic moment is aligned, this whole mineral as a whole, the mineral as a whole will not exhibit a magnetic behavior. However, when you introduce a magnetic condition, or you introduce a magnetic environment, you place this mineral exhibiting this paramagnetic behavior in a magnetic environment, this alignment is resumed. You would then establish an alignment in this magnetic moment, and thereby making this particular paramagnetic material magnetic. So essentially what we have is, we have diamagnetic material wherein you have pair of electrons cancelling out each other, no magnetic moment. You have paramagnetic material wherein, even though there are unpaired electrons offering you net magnetic moment, because these magnetic moments are randomly aligned, you don't see a magnetic behavior in the mineral as a whole. However, when you place it in a magnetic environment, this mineral begins to exhibit magnetic behavior, because in such a case, within a magnetic environment, these magnetic moments are aligned. So only difference between a magnetic behavior and the paramagnetic behavior is that these net magnetic moment within the entities, they are not aligned, and we can align them in a magnetic environment. That is what we refer to as paramagnetic. Para meaning close to, so they exhibit a behavior that is close to an actual behavior, and because the alignment of the net magnetic moment are not they are not similar across the different entities. Now, if in itself, within a mineral itself, if the net magnetic moments are aligned, you end up with ferromagnetic material. So the ferromagnetic material is when you have net magnetic moment, and you have this net magnetic moment because of the unpaired electrons, and these magnetic moments are aligned. So the combination of these two, net magnetic moment and a regularly aligned magnetic moment, leads to the ferromagnetic behavior. So what difference is between the paramagnetic and ferromagnetic is that ferromagnet, because it's already the net magnetic moments are already aligned, so they exhibit quite strong magnetic behavior. And on top of it, when you place both paramagnetic and ferromagnetic mineral in a magnetic environment, ferromagnet they sustain the magnetic behavior. Whereas once you remove the magnetic environment, ferromagnet, it sustains the magnetic behavior. In case of paramagnetic, once you remove the environment, it loses the magnetic properties. So that is one of the key difference between paramagnetic and ferromagnetic. So as a whole, the magnetic behavior, it stems from the rotation of the electrons. So within an orbital, we have a combination of two electrons, they are rotating in an opposite direction, so therefore they cancel out each other. Whenever you have orbitals, elements with orbital with a couple of electrons, then there is no net magnetic moment. However, when there are unpaired electrons, there is a net magnetic moment. So this is referred to as Bohr's magnetic moment. So there is a net magnetic moment when you have an unpaired electron, but because you don't have a counteracting rotation of electrons, but your mineral to be ferromagnetic, completely magnetic, the net magnetic moment should be aligned. If it is not aligned, you end up having paramagnetic mineral. Now both these ferromagnetic and paramagnetic, both these minerals, they behave like more or less the same in the presence of a magnetic environment. However, when you remove the environment, the ferromagnet will continue to remain the same. It will continue to exhibit the magnetic behavior, but not the paramagnet, because in ferromagnet we have the alignment of the net magnetic momentum. So with this, I would like to wind this lecture up. Whatever properties that we have missed in this lecture, whenever we are talking about the processing technique, we will touch upon that property that are relevant to us. So from the next lecture onwards, we will move on to considering or introducing ourselves to the different processing techniques that are involved in mineral processing. Goodbye.